Solubility-Product Constant. We can apply this idea of equilibrium to ionic compounds dissolving. And what we call the solubility-product constant, or KSP, is just the equilibrium expression for the chemical reaction showing an ionic compound dissolving. And a couple of things to remember, we've talked about equilibrium constants before, and it's the same idea, we're just giving it a special name. In the equilibrium expression, we do not put solids in the expression because the concentration of a solid doesn't change, and so we decided to leave them out. If we have a large KSP, it means the compound's very soluble. If we have a small KSP, it means the compound is not very soluble. So let's look at this. To do stuff like this, we first need the chemical reaction, and we show the solid compound in equilibrium with its dissolved aqueous ions. So here we have barium sulfate, and when barium sulfate dissolves, it's going to come apart into its ions. In this class, there's always going to be two different ions, one cation, one anion. So don't try to do barium, sulfur, and oxygen, just two ions. So there's barium. Barium forms a 2+ ion. We know that from the periodic table. And the rest of it, the SO4, stays together. That's sulfate ion. We should memorize the charge on that, but if you don't know it, you could figure it out from the barium. Bless you. Then we write the equilibrium expression. So we called it KEQ before. Now we're calling it KSP for solubility product. And so we take the concentration of the reactants, so here in brackets, the concentration of barium and the concentration of sulfate. And if there were any coefficients, then those would become exponents here. Now normally we would draw a line and then we would put the reactants underneath. But in the solubility product constant expressions, or the solubility product expression, yeah, I've heard it both ways. The reactant's always a solid, and so that gets left out. So these are not going to be fractions, which is kind of nice for those of you who don't like fractions. These are some solubility product constants. These are numbers that are just available on the internet and in large books and things, and they're just constants, and we use them as reference values, and so you don't need to memorize any of these. You don't need to put them on your little note card for the exam either. If you need a solubility product constant, I'll give it to you, either in the problem or as a table that you can refer to. So if we look at these, we see that the values for KSP vary, but they are all pretty small for these guys. This one's really small, 1.27 times 10 to the minus 36. So that's a really small constant. So let's look at that. For copper sulfide, what was copper 2 sulfide? So copper 2 sulfide would be CuS, that's a solid, and that's in equilibrium with the two ions, copper ion and sulfide ion. And so the expression for KSP is going to be the copper ion concentration times the sulfide ion concentration. So if KSP is a very small number, what does that tell us about the concentrations of the ions? Are they big or small? If you take two big numbers and multiply them, do you get a big number or a small number? You get a bigger number. If you take two small numbers and multiply them, you're going to get a smallish number, right? So when KSP is very small, that means that the equilibrium favors the reactants. It means that very little of this dissolves. And if we look these guys up in our table of solubility, the solubility rules, we'll see that most of these guys would be identified as being insoluble. And copper sulfide is definitely one of those. So let's write KSP expressions for each of these ionic compounds. What's the first thing we have to do? You have to write an equation. So we've got silver iodide. So we imagine putting that, a lump of silver iodide as a solid, into a beaker and pouring water on it. And then if that dissolves, what ions are going to form? Well, there's only two elements here, right? So we must have silver something with a charge. That would be aqueous. And iodide with a charge. What's the charge on iodide? It's 9. -1, right? So we look on the periodic table, we start with the noble gases, and we count over to the left. -1, there we are, iodide. What's the charge on silver ion? There's two ways to figure this out. Look at the formula here. There's 1 silver and 1 iodide. The iodide has a -1 charge, the silver must have a +1 charge. So that's one way to figure it out. The other way is, on the periodic table, we learned a little trick. Aluminum's in group 3A. It has a +3 charge. And then we imagined walking down the stairs. Aluminum's +3, zinc is +2, silver is +1. Those are the two transition metals that don't use a Roman numeral because they only form one kind of ion. Silver is always +1. Thankfully, though, you can do these problems without getting the charges correct. So there's our equation. And then from this, we can write the expression. KSP equals, we're never going to include the solids, so those guys don't come in at all. And so we've just got the products go on the top. And so it's concentration of silver ion times the concentration of iodide ion. There are no coefficients here. Because this was balanced without coefficients, one molecule of this would yield one of these ions and one of those ions. And so the exponents are 1s, which we also don't need to write. Any questions about that one?
So it's just writing an expression, not like solving it?
Right. At this point, it's just saying write the expression.
Okay, and the expression is based on the product.
The expression is based on this chemical formula. It is an equilibrium constant. And what we learned for equilibrium constants is you take each of the products and you put brackets around it to indicate the concentration in moles per liter. If there's a coefficient, you put that as the exponent. So if there was a 2 in front of silver, I would have to square this. And then you divide by the reactants. But solids and liquids don't change concentration, and so we leave them out. For one thing, it's a pain. It would be a real pain to have to figure out the concentration of all of those different things. And they're not changing it all, so it doesn't really matter. So we decided, it would just be simpler if we left those out. Well, I wasn't involved in that decision, but they decided that. So this next one, calcium hydroxide, we also need to write a chemical equation. So we take our ionic compound, and there's a solid, and we're going to think about adding water to that, and then we split it into the ions. What two ions are in calcium hydroxide? Calcium ion, which has a 2+ charge, and hydroxide. Hydroxide is one that you're supposed to know. Is this equation balanced? No. These generally are pretty easy to balance. If we just look at the formula here, 1 calcium to 2 hydroxides. So we need a 2 on this guy, and then everything's going to be okay. So for this one, KSP equals what? Calcium in brackets. Does that have an exponent? No. And then the hydroxide in brackets, right? Does that have an exponent? It's going to have an exponent of 2. It's squared because it has a coefficient of 2. whatever this coefficient is becomes the exponent on that concentration. Calcium here has an implied coefficient of 1. And here it has an implied exponent of 1. You raise something to the first power, though, it's just itself. So we don't need to write it there either. Any questions? Well, we can use those solubility product constants to determine molar solubility. And by molar solubility, we mean the amount of compound that dissolves in a certain amount of liquid. So molar solubility is the number of moles of a compound that will dissolve in 1 liter. So essentially, it's how many moles per liter. Moles of compound that will dissolve per liter. So let's look at this example. So here's silver chloride, and we've got the balanced chemical equation there for it dissolving, and we have KSP, and we need to find the molar solubility, which is frequently abbreviated as a capital S. So what can we do here? We want to know how many moles of silver chloride dissolve in a liter. That's what molar solubility is. We're going to need the solubility product expression, which we just practiced doing. So we've got product 1, the silver ion, and the other product, the chloride ion. Neither of them have coefficients, and so they don't need exponents here. And this is our expression. Now we're given the value here, so that equals 1.77 times 10 to the minus 10. Well, is that telling us how many moles of silver chloride dissolve? Not really. It looks like we've got 2 variables there, doesn't it? Well, let's think about what's going on here. Let's think about this as a pair of shoes. And there's a left shoe and a right shoe. If you have 1 pair of shoes, how many left shoes are there? 1. And how many right shoes? 1. It's equal, right? What if you have 10 pairs of shoes? How many left shoes? In 10 pairs of shoes? 10. And how many right shoes? 10. What if I had 5,000 pairs of shoes? How many left shoes? 5,000. How many right shoes? 5,000. How do we know that? Well, because a pair comes in with a left and a right. Yes? These ions come in as pairs, a positive and a negative. The ratio in this formula is 1 to 1. Now, other formulas are going to be different, but this one is 1 to 1. So that tells us that the concentration of silver ion must be equal to the concentration of the chloride ion, right? Because for every silver ion, you get a chloride ion from 1 molecule dissolving. Just like if you have 3 pairs of shoes, you're going to get 3 left shoes and 3 right shoes. And that is actually equal, well, we're going to call that S, and that is equal to the moles of silver chloride that dissolve per liter of solution. Because the number of left shoes is equal to the number of right shoes, which equals the number of pairs of shoes. That make sense? This isn't trickeration, this is math. Although sometimes math looks that way. So this is S. So this is S. So what happens in this equation? So I said silver is equal to chloride, and they're equal to S. So in this equation, instead of silver ion, I'm going to write S. And instead of chloride ion, I'm going to write S. Because they're equal, right? So then what do we have left here? We've got S squared is equal to 1.77 times 10 to the minus 10. So what does S equal? How do you undo squaring something? Square root. So to get this to S, I need to take the square root. Now be careful in your calculator, because if you don't enter your scientific notation correctly, it'll mess you up. Not a one-handed calculator. It is also not a calculator that actually wants to turn on. Yeah, there we go. Nothing like a little convincing. So when I do that, I come up with 1.33 times 10 to the minus 5. That is equal to the concentration of silver ion, which is equal to the concentration of chloride ion, which is equal to the number of moles of silver chloride that dissolve per liter. And so the units on that should be capital M for moles per liter. We're not going to get crazy about units right now because I haven't taught you about moles per liter yet. That's coming. Any questions on how I solved the problem? Yes?
Where did you get S squared?
Where did I get S squared? I got S squared because here I've got S times S. So I had the silver ion concentration multiplied by the chloride ion concentration, but I recognized that they were equal to each other. And so I said, well, I'm going to call them S. So then I can substitute S in for the silver concentration and for the chloride concentration, and S times S is S squared. Any other questions? Here's another example. Calculate the molar solubility of calcium sulfate. We're going to need a number, though, aren't we? We need some sort of a number, yeah? Well, before I start writing and can't go back, I'm going to go back. Calcium sulfate. Right here. Calcium sulfate. The solubility-product constant is 7.10 times 10 to the minus 5. We're going to need that number. So KSP equals 7.10 times 10 to the minus 5. And that's how you find that out. You just go look it up. So molar solubility of calcium sulfate, we're going to do the same thing we did with the silver chloride. We need the expression. We know that the expression is equal to this number, but we need to get the expression, and we get the expression by looking first at the chemical equation. So calcium sulfate in equilibrium with its ions. Calcium ion and sulfate ion. Now that we have the equation, we can write KSP expression. What do we do? We take the concentration of this product times the concentration of that product. Wow, you guys are sleepy. Every time I look up, somebody's yawning. You're gonna get me started. I hope that means you had too much fun over spring break. In this equation, there are no coefficients. This formula, 1 calcium, 1 sulfate, forms 1 calcium, 1 sulfate. and this guy's a solid, normally we would divide by the reactant, but it's a solid, so we leave it out. So there's our expression. And we know that that is equal to 7.10 times 10 to the minus 5 because we looked it up in the table. What do we know about the relationship between the calcium ion concentration and the sulfate ion concentration? They're going to be equal, just like the left shoes and right shoes in a pair. So we know that that's not Ka, calcium, C, that's a C. Ca equals the concentration of the SO4 2-. And let's call that S. So I'm going to do that same thing. Here's S. Now back in that equation, I'm going to put S in for the calcium ion concentration, and I'm going to put S in for the sulfate ion concentration. Because they're equal. I'm just calling them both S. There's some number that I don't know, but I know it's the same number. So we're calling it S. S times S is S squared. And so we end up with S squared being equal to that solubility product constant. Then we're going to take the square root of both sides. The square root of S squared is just S. And so S equals the square root of 7.1 times 10 to the minus 5. (7.1) EE minus 5 square root 8.43. 8.43 times 10 to the minus 3rd. And we're just going to slap a unit on that of molarity. There are other problems that get much more complicated. Both of these examples have been where there's one cation and one anion. And so we can do this and it ends up being S squared, and we just take the square root and it's easy peasy. There are other things like calcium chloride where you've got 2 chlorides and 1 calcium, and then mathematically things get a little bit hairy. So we're not going to go there in Chem 20. But this will get your feet wet if you need to go on and take Chem 1. They're going to go there. They're going to go, and you may have to do quadratic equations. A guy this morning almost fell out of his chair when I said that. We're not doing quadratic equations, but you may have to do that. But at least you'll be familiar with the whole idea of the equilibrium expression and an idea of how to solve them. So we're only going to do ones where this is a 1-to-1 ratio. And so basically it comes down to the solubility ends up being the square root of the solubility product constant. Any questions?
What about the products that are always going to be solid?
Pardon me?
Are the products always going to be, the reactants always going to be solid?
The reactant's always going to be a solid.
Okay.
Yeah, because it's the equilibrium between the solid and its dissolved ions. And so the reactants are always a solid.